Hi, we're Group 12 and today let us take you through our L2 application journey, which was to design, manufacture and test a wind turbine. A wind turbine is a device that captures wind energy and transforms it into kinetic energy via the rotation of blades which can be used to power a generator. Such devices are becoming increasingly important as a renewable source of energy. The challenge posed to us was to design and manufacture a two-blade wind turbine that is no heavier than 500 grams and has a maximum diameter of 800 millimeters. When it is tested, it has to self-start at a wind speed of less than 10 meters per second, and its maximum CP should be achieved at a tip speed ratio that is between 3 and 8. Also, the maximum revolutions per minute should not exceed 3000 RPM. Due to the design of the test rig, the wind turbine is required to rotate anti-clockwise. With this criteria in mind, we began our first step, which was the design process. We began by deciding on a suitable tip speed ratio, also known as TSR. After extensive research on small two-blade wind turbines, we decided to base our design on Professor Graham's recommendation of a TSR of 4. Following this came the choice of aerofoil. This was a source of constant deliberation, as there were many options to choose from. Making use of data from online databases, we compiled a short list of 12 potential aerofoils which could be used for this challenge. Out of them, 2 were chosen. S835 was used as the root and SG6043 as a primary aerofoil. After deciding upon a root length to be approximately 10% of the radius, a model of the chord distribution was made, where the chord length was approximately proportional to the inverse of the radius. The pitch or twisting angle for both aerofoils was then determined using the following formula. Having determined the optimum angle of incidence when choosing the aerofoils, the twist of the entire blade could be calculated. The tapering of the primary aerofoil and the root was done in a manner such that the calculated pitch angles could still be preserved. Calculations for the structural stresses were carried out using beam theory, and all the stresses were found to be less than 21.6 megapascals, which is the peak tensile failure stress of ABS plastic, the material with which the wind turbine is made from. When designing the cone, the aim was to reduce the drag and weight. This was achieved by using the Huck series to construct a cross-section of the cone and extruding it 360 degrees, followed by hollowing it out. The manufacturing process was split into 2 main parts, the hub and the blades and cone. The first step in creating the hub was the turning process, where the lathe was used to produce a circular shape. Material was progressively removed as the aluminium block rotated. Then milling was performed so as to achieve the desired square shape of our hub. Following this, threading was done so that the cone could be firmly secured to the hub. The final step was to broach a keyway through the hub to ensure the wind turbine will be locked together with the test rig. The blades in the cone were manufactured using the 3D rapid prototyping method, and the material used was ABS plastic. Once everything was completed, the pieces of the blade were glued together while being held by clips. After a week of curing, sanding was done to make the surface of the wind turbine smoother, especially at the dovetails where the glue was applied. After weeks of exhausting our brain juices and intense manual labor, our final product was ready to be tested. In a corner of Roderick Hill L50, standing at 759.24 millimeters, weighing at 368.2 grams, Group 12 presents the wind turbine with black outlines, aka WT-WBO. On March 7th, WT-WBO made its debut performance in the Honda wind tunnel at wind speeds of 6, 8, 10 and 12 meters per second. WT-WBO self-starting at approximately 4 meters per second, well below the design requirement. We were further buoyed by the comments of the lab technicians, who commented that given our low weight, we were achieving good maximum power coefficients at 6, 8 and 10 meters per second. But alas, all good things must come to an end. Unfortunately for us, the end came a bit too abruptly. In its valiant attempt to endure the 12 meters per second winds in the tunnel, WTWBO ended with a loud "Oh!" Feeling dejected, but determined to find out why WTWBO failed, we went home to analyze our results and the wreckage. After analyzing the results, it was noted that at wind speeds of 6, 8 and 10 meters per second, the maximum CP value occurs at a TSR value of 6. This is in spite of the fact that the initial constraint of our design was at 4. Also, after careful analysis and observation of the wreckage, it is noted that the blade had broken off at the root, where the dovetail connects the casting to the blade. After further analysis, we have managed to narrow down 3 key areas of discussion. Firstly, the TSR. One key aspect of our results is that the tested value of the TSR is approximately 6, which is not the same as our design value of 4. While this may seem very wrong, the tested value of the TSR does actually correspond to various literatures, whereby the optimal TSR for a 2-blade wind turbine is approximately 6. Also, throughout this design process, compromises had to be made. One such compromise came when choosing what aerofoil to use for this challenge. The S835 is a very efficient root aerofoil for wind turbines from 1 to 3 meters in diameter, while in our case, the wind turbine designed is smaller than 1 meter. Also, various values such as A0 and A1, which are important elements in the design process, have been assumed to be a certain value. For more accurate results and better designs, experimental testing for these values should be done. Next, another obvious area to discuss would be the reasons behind the structural failure of our wind turbine. One possible reason could be that we failed to take into account the effect of the stress concentration caused by the sharp edge of the dovetail on the overall stress distribution across the blade, especially at the root. When the calculations for the stress distribution were made, it was deemed to be within the limits of the ABS plastic. However, the presence of the dovetails would have increased the stress concentration at the root. This would have added to the already high stresses that were present at the root, causing failure. Our calculations also neglect torsion due to aerodynamic forces, which might have a contributing factor in the failure of the structure. Also, there could have been some form of defect in the gluing at the root. As seen from the broken pieces, it seems that the crack initiated from the gap at the trailing edge, where the glue should have held the components together. This is seen from the smooth, then abrupt change in contact surface. Hence, this suggests that the crack propagated towards the leading edge, and when it reached the point of highest stress concentration at the dovetail, it caused the blade to break. The sudden loss of one blade caused an imbalance of angular momentum, which would have resulted in the second blade breaking off as well. Finally, the maximum CP achieved by our wind turbine is 0.214 at 10 meters per second. Comparing this to that of a well-designed wind turbine, which can have a maximum CP of 0.35, it is clear that losses are present. One such loss is at the blade tip. Generated vortices lead to a reduction in the free stream speed of the air just in front of the turbine, thus reducing the power absorbed by the turbine. Another loss would be due to wake swirl. Since our design was based at a TSR of 4, when the turbine was spinning at a TSR of 6 in the experiment, the rotating blades were passing through air which was turbulent, hence a decrease in power extracted from the wind. At the end of it all, there are always areas for improvement. Values of A1 and A0 should have been experimentally determined instead of using approximated values. This will ensure that the design process is performed to a greater degree of accuracy, thus leading to better approximations of the expected results. On the issue with the reduction in power transferred to the wind turbines, the tips of the blades could have been better designed to push the vortices outwards. This reduces the drop in free stream velocity just in front of the blades, and hence more power is transferred to the turbine. The use of beam element momentum theory can also be used to attain a more accurate approximation of the performance of the wind turbine, as well as the loads that it may be subjected to. Finally, taking a more radical step, alternative materials such as fiber-reinforced polymers can be considered, as they tend to have better material properties. To round it off, having come full circle, this L2 journey has been a fruitful and rewarding one. As the old Chinese saying goes, Shi bai shi, Chen gong ji mu. Failure is the mother of all success, and this exercise, though not entirely a failure, will spur us onwards, hopefully on a stable state space towards success.